Hi, it's Anthony again, and today we're going to be talking about PCA, which is probably the most commonly used dimensional reduction technique in machine learning, and I've seen it used a lot in industry, and so it merits diving in a little deeper to try to understand what's actually going on and understand how it works, because then you can better understand the limitations. So that's basically the goal of this video, to show PCA technique. So we have a lot of data that's in many different dimensions, let's say like 10. You want to get it down to something that's maybe more manageable for whatever your application is. This could be a technique that could help you. So in this video, we want to look at how does it actually work for real. So a lot of the tutorials that I've seen online are very superficial. So I want to try to dive a little bit deeper into it. So basically the key thing is that we want to transform our data into a new coordinate system which maximizes the variation in the first dimension. So we're going to look at it like, what does it mean to transform the data? How does PCA actually maximize the variation? And again, show how it really works. And to accomplish that, these are what we're going to do. So first, we're going to generate some data and plot it. We're going to normalize our data, which is key for PCA to actually work. We're going to show that whatever data matrix we have, that's the representation of our data, if we multiply it by its transpose, that's going to give us the covariance matrix. We're just going to empirically show that without a proof, but seeing that is still pretty interesting. We're going to also try some random transforms just to kind of demonstrate like what a transform actually is. So we're going to take our data, multiply by a 2x2 matrix, so our data is going to be just xy pairs, and transform it using this 2x2 matrix, and then see kind of what happens. So then the key thing for PCA is to figure out what transform of our data would actually maximize the variation in the new coordinate system. And we're going to just take a quick, more proof type look at some of the math behind that. We're not going to actually show it, but we're just going to look at some pages that show that. Then we're going to actually code this all up. So we're going to implement our own PCA. So the first thing is to find the eigenvectors and eigenvalues of our data matrix, of our covariance matrix, which is based on the data. Then we're going to arg sort the eigenvalues so that we get the largest one first, and also sort the vectors in the same way. Then we're going to generate a column matrix of putting together the different eigenvectors in this particular order. So we want the eigenvector with the largest eigenvalue first. Then we're going to matrix multiply our data by this new matrix that we came up with. We're going to plot the results, and that should be the essential parts of PCA. And we can check it by comparing it to the scikit-learn's PCA. All right, so that's a lot to cover in one video, so let's get going. Okay, so the first thing we have here is we've made some points, some xy pairs. So you can see it's basically a simple parabola, and we've added some noise. Also, we've added a color here, which could potentially be another dimension, but it's just going to help us with the visualization to show the general shape of, or just to show how things are moving maybe a little bit easier as we transform our data around. So next we're going to normalize our data. Okay, so we've normalized our data. It hasn't really changed it too much. These y values have shifted down a little bit from before. That's because when we talk about normalization, we're saying that we're subtracting the mean and dividing by some, either like the standard deviation or the variance. And here we just use the variance. All right, so next on our list of things to do was how we can get the covariance matrix by multiplying the data by its transpose. So let's do that. So first, let's calculate using the numpy covariance matrix function and find out what the actual covariance should be. All right, so we use the numpy function for covariance right here. Then I got my value. And then I divided by the max just to normalize my output values. Here, I'm taking my data and I'm multiplying by its transpose to get this data conv cov 2. It's not a convolution, but it's a covariance. And then I'm going to also divide by the max again. And you can see the normalized representations of the two matrices are equal. And so this is just demonstrating that this is another way that we can easily get our covariance matrix using the transpose and matrix multiplication. All right, next on our list of things that we want to do is matrix multiply the data by some random 2x2 matrices to transform it into a new coordinate system and see what happens. This will help us kind of visualize what happens when we transform our data. So let's go ahead and do it. All right, so we've coded opcode here to just multiply our data by a random matrix. So this is random transform into a new coordinate system, and then we plotted it. So my first figure right here, or my first subfigure, this is the original data, and then in all the remaining ones, we are just generating this random 2x2 matrix. So we take a look at the last one. This is what it looks like. And then we're going to matrix multiply our data. So this is 2x2 is the size of A, and then data has a size of 2 by 200. So the last dimension of the first matrix and the first column of the next matrix need to be equal. So 2 and 2. That's why we can multiply them together. Then we get this data 2 out. It's going to have the same shape as data. We can show that by just looking at it. And so we can plot it again, and we can see how our data has shifted. And you can see why the color was maybe a little helpful now, because it wouldn't necessarily be clear how it was transformed, but the color kind of helps us out a little bit. So clearly we can change the representation of our data in a lot of different ways to get a new interesting coordinate system. So really the goal of PCA then is, these are some candidate transformations that we could apply, but it doesn't mean they're actually going to be helpful. Instead, we want to find a transformation that is helpful. And what we mean by helpful is the one that maximizes the variation of our data in its first dimension. So the thinking is that we could go all the way down to just one dimension. So if we had start with like 10 dimensions, like hair color, height, weight, or something else like that, then you might want to reduce it all down to 1. This could be a technique where we could do that, and the goal is to capture as much information as we can in that first dimension. And so we need to find a matrix A, which is going to be helpful. One interesting thing that we're going to see in a minute is that our matrices are going to be orthogonal, or the transformation that we're going to apply are going to be from an orthogonal matrix. So potentially we could try making each column orthogonal and kind of see what happens. So let's try that real quick and see if we notice any differences. Okay, so we've found two orthogonal matrices by finding the eigenvalues, which we're doing here, and then we're just going to use those instead. So eigenvalues by definition are orthogonal. Our data 2 is then an orthogonal transform of our data, and orthogonal means it's preserving the idea of being perpendicular. So this is why it just looks like rotations. So moving on, our next step was, so we finished 4. Now we want to talk about what matrix transform and maximize the variation in our data into a new coordinate system. So in PCA, we find that the first eigenvalue or first eigenvector of the covariance matrix is the transform that will maximize the variation in our new coordinate system. So we want to actually show that that's the case. So this is where it gets maybe a little bit tricky, and I'm going to refer to Wikipedia here just to show what's going on. So imagine we're given a data matrix X, and we want to multiply it by some weights, multiply into a new, basically move everything into a new dimension. That's going to give me t, so x times w is going to give me t. So really what this comes down to is then finding a w which gives me the argmax of this t. Now the reason why, so this representation here is the variance of t, which when I first looked at this was a little confusing because like we're not subtracting the mean or dividing by the variance. So like how is it that this is the case? So one detail that it talks about above, 0 is the mean, so we don't have to subtract it off anymore. So this is the variance representation. So the idea is find a vector w which gives the maximum variance. So we can decompose this t, which is simply x times some weight. Then we can put this in a matrix form, which is what they're showing right here. Then we can multiply by, we can take this square and expand it so that we're doing the weight transpose times the x transpose times the x times the weight. Then because earlier we said that this is going to be a unit vector, we can just divide by 1, and the unit vector transpose times itself should be equal to 1. So this is the same thing shown right here. Now they say the quantity to be maximized can be recognized as a Rayleigh coefficient or quotient. So then that brings the question of like, well, what is a Rayleigh quotient? So if we take a look then at the Rayleigh quotient page, we have all this stuff up here. It's kind of confusing, but then they have a special section about the covariance matrix, which is really kind of what we're after. So it says an empirical covariance matrix M can be represented as the product of A transpose A of a data matrix A pre-multiplied by its transpose. So this is maybe a little confusing. Here they have T as the transpose, but here they're just giving it the single quote. So then we know that here x transpose times x, this is the covariance matrix. That's what we showed earlier in the video, that we could actually do this. So if that's the case, then we have this w times the covariance matrix times w is, we're trying to find the argmax of that, of whatever's in there. So then there's a few ways you can think about it. So they give one approach here, which personally I found this a little bit confusing. However, I found the Lagrangian multiplier method a lot easier to basically understand. So they basically do the same thing, or they talk about the same thing, and also they say that they basically make it into the Lagrangian form. So Lagrangian form is just a type of way of taking a constrained optimization problem and making it into an unconstrained equation that might be easier to solve. Sometimes it's easier to solve. So the way that you do that is you add in this Lagrangian multiplier times your constraints. So this xt, that's our weight, m is our covariance matrix. We already basically solved that. X is our weight, or our vector weight. And then lambda here is some constant that we're just inventing basically to make it easier for us. The constraint for this optimization problem is that this x has to be equal to 1, that it's a unit vector. So we can use that to our advantage. You might be thinking like, well, why is this an optimization problem? So finding the max of something is basically an optimization problem that you're flipping to be a maximization problem. So here we've added our constraint in, multiplied by Lagrangian multiplier. And what we can do is then do our normal optimization methods. We want to find the stationary point. We can do that from like Calculus 101 by finding the derivative of this with respect to our variable. So we're going to find it with respect to x, which is what we're doing here. Then we just simplify some terms, and then we get this mx equals lambda x. Now, if you're familiar with what a eigenvalue actually is, then that should look quite familiar to you. So an eigenvalue means when we multiply something by when we multiply our matrix times a vector, we get a scalar representation of that same vector. So let me paste that in real quick, just so I have a better idea what's going on. All right, so this is the definition of an eigenvalue. A times v, okay, A is our data, times some vector v that we want to find equals a scalar times v. So this is actually really important for a lot of engineering applications, including the one that we're looking at now. We can simplify this so that we do a times v minus I times lambda. And this becomes something that we can solve, and also can be helpful for giving us the characteristic polynomial for this particular matrix. So basically what we did back with this Rayleigh quotient, when we use this Lagrangian multiplier method, we got it in this form where we're saying, hey, find x so that when you take your data and matrix multiplied by x, you get a scalar representation of x, a scaled x. So that means just find the eigenvalues. So rather than dive into all the details of actually like how do you find eigenvalues, it's not really the point of this video. You can look it up in many references online. But the key thing from a just computational standpoint is that this is actually easy for us to get using standard libraries in our toolkit. So I can easily ask NumPy to calculate the eigenvalues for me and then see what they actually are. So that's what we're going to do. We're going to get the eigenvalues and the eigenvectors that go along with them. So the eigenvalue is the lambda here that goes along with this v, and v is the eigenvector. So, and then we're going to sort the eigenvalues by their size so that we get the largest one first. Then we're going to take all the v's and put them into a matrix, and this will be the matrix that we want to use to transform our data. So let's get coding. We've gotten our eigenvalues. We sorted them, and then I plotted them just to see what direction they're going. You can see they're orthogonal to each other. So next we just need to take our data and multiply it by our matrix that's composed of eigenvectors. So let's go ahead and do that. All right, so I found I made a mistake. The key thing is that if we take a quick look at this eigenvalue calculator, it says it's going to return the weights and then also the vectors, where the normalized eigenvector is such that the column is the key, that it's getting columns. So when we do our sorting here, we want to get all the rows and then a particular column. And this will give us the correct representation. So with that in mind, let's keep going. Okay, so we've plotted our data. It doesn't actually look that much different. So to make something that looks a little bit different, let's change up our original function. So it's not just a parabola. I think this will be more interesting. So let's go back to the top, and I'm going to change how we generate our data. So I made a new function here. I don't know if it's a whole lot better, but it's a parametric function. So we define some t value, and then x and y are both functions that operate on t. And you can see it's just a sinusoidal like function for both x and y, which means we could do something like a circle if we wanted. So then when we do our transforms, so this is our orthogonal transforms, you can see we can rotate it around in various different ways. It's kind of interesting. Then when we apply our PCA, we get something like this. So the final step is we want to see if we actually got this right. We can check our work by comparing our results to scikit-learn. So let's go ahead and try that. And there we go. If we plot our two results, you see that they have basically the same result, which is good. Let's try to find a simple function which better shows the PCA. Okay, so this function is a lot simpler. It's basically just a line, but you can see that the maximum variation is in this direction, which we can, by looking at the equation, we can see is just we'll have a slope of 2. So the vector 1, 2. So let's see what happens when we do our transforms. It's also interesting looking at these transforms, seeing they get squished for some of them and spread out for others. And then our representation of the data has been transformed significantly. We can see that the scikit-learn's representation of our implementation of PCA was basically the same thing as what we got, which is good. We have correctly reduced our data down to the form that we want. And that's all for today. So that was kind of my dive into understanding how PCA works, and I hope that was helpful for you as well to kind of just work through the code, see what's actually going on, and think through some of the concepts.